installation permits and licenses. And finally, determine the method of traffic control and rerouting that will take place during the installation. This traffic control and rerouting method includes the position and quantity of barricades and cones. The information obtained from this initial visit is then incorporated into the plan drawings. A second field visit should be made to verify the accuracy of the completed drawings. If the installation is to be performed by an in-house crew, the next step is the estimation of manpower requirements. Studying the plans, determine the scope of the installation work, the amount of time required, and the size of the crew. Often a crew should perform certain installation tasks simultaneously to reduce the time that traffic is disrupted. The equipment required by an installation will in effect be dictated by the detector system type and configuration. Check your handbook for details, including a list of equipment necessary for a typical loop installation. And don't forget that barricades, signs, cones, safety vests, and other devices will also be required to control traffic during the installation. When determining an installation's material requirements, assure that all materials are provided in large enough quantities to avoid any work interruptions. A typical material list for a loop installation includes detector wire, lead-in cable, pull boxes, sealant, cement, sand or talc, concrete, surge voltage protector, solder, splice kits or equivalent, and spray paint or chalk and line. This completes the pre-installation process. Now let's discuss installation techniques using our example for illustration. As detailed in this schematic, the loop detector system is composed of one or more wire loops embedded in the pavement to act as a sensor, a splice between the lead-in wire and the lead-in cable in the pull box, the lead-in cable, which is usually in a conduit running to the terminal strip in the controller cabinet, a cable from the terminal strip to the electronic detector unit, and finally the electronic detector unit itself. Installation techniques and theories vary widely among traffic agencies. Construction supervision and inspection by the responsible agency is critical. Let's examine the basic steps to a loop detector installation. Loop detectors are installed in asphalt or concrete pavement by cutting a slot, cleaning and drying the slot, laying in and testing the detector wire, sealing the saw cut, connecting the wire to the lead-in cable and testing it, connecting the cable to the terminal strip in the cabinet, and ensuring that the harness connects the terminal strip to the electronic unit. We will look at each of these steps in detail. Differences among installation techniques usually involve the treatment of the corners where two saw cuts intersect, the splicing techniques, the type of sealant, and the method of applying the particular sealant. Whatever the technique, following accepted procedures will help guarantee the detector's long-term effective operation. Long-term effective operation is the goal. The large number of loop detector failures nationwide has created a deep concern within the traffic engineering community. A number of studies have traced many loop detector failures to a problem with the in-road loop wire, or to the splice between the lead-in wire and cable. These failures are usually due to bad pavement conditions or sloppy installation techniques. Several state agency surveys have noted that at any given time, up to 25% of their installed loop detectors are not operating properly. Now, using our 6-foot by 30-foot quadrupole loop example, we will discuss loop detector installation basics step by step. For more details as well as information on loop installation alternatives, please refer to your handbook. The first step in our detector installation is loop layout. After securing the work zone, carefully mark the pavement for the loop size and shape as detailed on the plans. This loop layout can be accomplished using a lumber crayon, chalk, or spray paint with a template. A straight edge or a tightened string can be substituted, however, as a marking guide. Loop corner treatments vary among agencies. Traditionally, the chamfer cut has been used to ease the stress of a 90-degree corner on the wire. This diagonal cut should be 12 or more inches back from the corner to prevent pavement breakup. As an alternative, however, many agencies choose to core drill holes at the loop corners. This corner treatment, chosen for our example, preserves the integrity of the pavement and the wire. Now it's time to saw cut the slot for the loop wire. This is one of the most time-consuming parts of the installation process. There are many saw types and sizes available. Durable diamond blades and fast-cutting, high-horsepower saws are recommended. Water cooling the saw blade increases its life and eliminates the irritating, dangerous, dry-cutting dust. Studies have shown that using a diamond blade, a high-horsepower saw, and water cooling reduces cutting time by 2/3 compared to the less expensive dry-cutting system. The slight increase in initial saw costs can be reclaimed in savings of time, labor, and equipment longevity. Regardless of the type of saw used, it should be equipped with a depth gauge and a horizontal guide to assure proper depth and alignment. Check the depth of the saw cut frequently to assure that it is constant. Although the appropriate depth depends on the number of turns of wire, a minimum depth of 1 1/4 inch and a maximum depth of 2 inches should be maintained. If your saw cut is out of alignment, do not make a second cut near the first. If a second slot is necessary, cut at least 4 to 6 inches from the original slot to avoid significantly weakening the pavement. Finishing the saw cut is an important installation step. Cleaning the saw cut, including removing all jagged edges with a chisel and hammer, should be done immediately after cutting. It is crucial that the saw cut is clean, dry, and free of dust, grit, oil, and contaminants. The recommended practice is to flush the slot clean with pressurized water, then dry it with compressed air. Take care not to blow any debris in the direction of passing pedestrians or vehicles. After the slot is saw cut and cleaned, it is ready for the loop wire. Many contractors have developed their own wire installation techniques and shortcuts. It is important to inspect these procedures during installation. If a wire is damaged during installation, it should be immediately pulled up and replaced. The most commonly used wire size ranges from number 12 to number 16 AWG. In our example, we are using number 14 AWG wire. Stranded loop wire is more likely to survive stretching and bending. The wire insulation must withstand wear and abrasion from shifting streets, moisture, solvents, and oils, as well as the heat of high-temperature sealants. Wire encased in continuous cross-linked polyethylene tubing is popular due to its durability, flexibility, and heat resistance. Some agencies pre-wind and bind loop wire to the exact specifications in their shops, making a prefabricated loop to transport to the site. Best suited for smaller loops, this procedure significantly reduces on-site installation time. Several detector manufacturers offer a pre-formed loop assembly that can be placed in existing pavement slots or installed in other ways during the construction of new roads. Although the initial cost of the preformed wire is higher, the total installed cost is often lower than that of standard loops. A metal sheathed loop, known as mineral insulated or MI cable, is particularly good for hazardous locations or difficult environments. This factory-assembled loop has several advantages, including an excellent shielding system. Wire insertion is the next loop detector installation step. The loop must be one continuous wire, from the pull box through the curb, around the slot the correct number of turns, and back to the pull box. Check the supply reel to make sure there is enough wire before beginning. It is very easy to lose count of the number of turns you have inserted, particularly with 4 or more turns. Pre-wound or pre-formed loops can eliminate this possible confusion. All loops should have enough turns to provide at least 100 microhenries inductance per loop. This is a simple rule of thumb for determining how many turns are needed to provide the required inductance. If the loop perimeter is under 30 feet, use 3 turns of wire. If the loop perimeter is over 30 feet, use only 2 turns of wire. When a loop is placed in a concrete roadway and crosses a pavement joint, particularly an expansion joint, the wire can be damaged as the concrete slabs move. The joint where the road surface meets the curb line can also cause problems through horizontal and vertical shifting. There are two basic treatments for crossing a pavement joint. One method is to encase the wire crossing the joint in some type of conduit, from a rubber garden hose to flexible or rigid plastic tubing. A second method is to provide extra wire at the pavement joint. For example, you can make a 2-inch diamond cut at the joint to allow an S shape of extra wire. After inserting the wire, you will have two lead-in wires from the beginning and the end of the loops. These two wires should be twisted together to form a pair from the loop to the pull box. Using a twister is a lot faster than doing this job by hand. To avoid crosstalk, you should twist the wire between 2 and 5 times per foot. And if you are installing adjacent loops, make sure you twist all the lead-in wires in the same direction. Typically, the twisted lead-in wire extends from the loop across the curb or shoulder to the pull box. The lead-in wires from adjacent loops should be run to the pull box in separate slots to avoid crosstalk. At intersections with curbs, the joint where the road surface meets the curb line can cause problems for the twisted wire through horizontal and vertical shifting. Using a jackhammer drill or punch-type tool, make a hole in the curb and install a watertight, flexible conduit. At intersections with shoulders, as in our example, dig a trench from the pull box location to the pavement. Then, at a 45-degree angle, core drill a hole at least 6 inches from the edge of the pavement into the trench. Next, cut 1-inch, thick-walled PVC conduit to the correct length and place in the core hole. Run the wire through the conduit and then the conduit above the drainage line to the pull box. Then place duct seal at the pavement end of the conduit to keep out saw-cut sealant and to facilitate any future maintenance on the wires. Refer to your handbook for other curb and shoulder crossing techniques. The next step is the installation of the pull box, also called the splice box, the junction box,